So in Microsoft Office 365, there will be occasions. We have a template, a Boolean template that would allow you to experience and or in not in a spreadsheet. And so you'd use Excel. You may or may not be familiar with a spreadsheet, but in order for that to work, you download the file. It's a .xls file. And if you don't have Office installed on your laptop or your PC, you're allowed 5 installations. This includes Access. So Access is a database, very powerful database. So that's an important add-on that is useful in a variety of settings in our course and in other courses. And so I just wanted you to be aware that sometimes when you're facing difficulties working simple things and you're at home, it may be that you need to connect and then sign in. Now, the unintuitive part of this is signing out. So if you are using the Outlook client for your email, and I use the Outlook client, and I have it set up in offline mode, it'll prompt you to sign in, but sometimes it just says disconnected down here. It doesn't explain that it still needs something, and it shows that it's disconnected. And unless you catch that, you're not going to clear the issue. So a lot of people think that the problem is with their laptop or with their PC. What's counterintuitive is to go to the file menu, go to the Office account, and then use the sign out option to manually force a sign out, and then when you're connected to the campus to sign in again. So this is just a helpful tip in case you face challenges with your Office apps. Any questions about the Office applications that we're using for some of our resources in this module? Okay, so I'm going to go ahead and click into Blackboard in case we have any questions about the material from our module. And we've got our study guide here. If you're clicking on these links, you'll basically get to the point where you'll meet and greet the textbook authors. If you haven't done so by this time, you really need to do so, right? You really need to click these links and watch what's going on and how things are working. Today, we're going to be continuing our exploration of binary operators, and we're going to dabble a bit in hex, just so you understand hex. Most of our time will be spent in the binary world working with Boolean and or not, but we are going to become familiar with hex. So yesterday we had a simple breakout of some examples. So if I have this in a Boolean number, a binary number, can anyone tell me what that number place, that's the 4th number place, can anyone tell me what the value of this number is?
Would it be 8?
It is 8. Excellent. So everywhere, yes. Welcome, Joshua. How are you?
No, I was here the whole time. It just disconnected and reconnected.
Right. Yes. We're going to remain vigilant in calling out this contradiction of verbal terms that you have to unlearn. So this is the symbol for and. This is not the symbol for and. This is the symbol for or, and or means addition in binary terms. So in any case, everywhere you see a 1, you have to multiply that by the number the place represents, and this is the 8th place. So this is the 1, 2, 4, 8. Can anyone recall what we call the common term for a 4-bit value?
A nibble.
A nibble, right? And 2 of those together is
A bite.
a byte, right? So somebody has a sense of humor. Yeah, somebody has a sense of humor. In this case, it's very important to remember these logical absolutes. So we explored the difference between and or. And essentially what you find out is that if just one of the inputs is true, then the entire output is true. If just one of the inputs is false for an and, then the entire output is false. We also learned that a not operator only has one input, will only ever have one input. Well, while and or can have 1, 2, 3, 4, 5, 6, take your pick, right? Number of inputs, you can create a logic gate with 27 inputs. But if you have a not in the mix, the not will always have one input and just one output. And it flips the value. So if you combine the not with other Boolean operators, we say that it creates a wildcard. The outputs are reversed or changed in a profound way depending on the placement, the physical placement of the logical gate or the Boolean operator. Now, we also explained the difference between Boolean operator and logic gate. Could I have a volunteer to unmute your microphone and explain the difference, the primary difference between a Boolean operator and a logic gate?
A logic gate is hardware, while a Boolean operator is software.
Excellent. Thank you very much. Yes, that's correct. So we always think of Boolean operators as a software concept. It's a software logic function. And a logic gate is, the word gate implies, like open and shut physical gate. And that's actually very true in terms of how it works. So what is this symbol over the letters here? Let's say that each of these are input variables. Let's say that we have 26 input variables. We have 26 on or off switches that represent binary values that are inputs for a given logic gate, a complex logic gate. Let's say it's a compound logic gate. And you'll see in a minute what happens when we start combining these things, right? Can anyone explain to me what this line over the variable label is?
It's a bar and it means not.
That's correct. Okay. Yes, I know the description is right here, but whenever you see the bar, it means you take the original value that's inputted into that. You take the original value that's stored in that logic gate or Boolean, the variable, right? So you have a variable, you have a software variable, or you have a logic gate. You take the Boolean value that is stored in there, and because the bar represents a not, you flip the value, okay? So yes, we want to make sure that those are firmly implanted in your mind before we continue. I would like to take a moment to kind of walk through what happens when you perform the steps of the solution, okay? So as you download the NAND to Tetris software, I like to unpack it and put it in a temp folder with the same name as the zip file. So all I do is highlight the name of the zip file without the extension. And then I double click it and unpack it and put it in here. Now I have an extra directory in here with additional PowerPoints. At some point of your exploration, if you're reading through the study guide and you're doing what you're supposed to, as you're following along through the module, you're going to see this PowerPoint, and it talks about the hardware simulator. And it talks about how that works. And it's important to take the time to read through this now, okay? Now, in simple terms, what it's going to do is explain or give you an orientation of this hardware simulation environment. And the code that is read by the hardware simulator is called an HDL file. Now, an HDL file is nothing more than a text file. So if I created a text file, saved it to a temp folder, right? Let's say that I put it in, I'll put it in here in our solution, module 1, and I'll say sample HDL. I'll put sample.hdl. And I put something in here. Yeah, I made it funny on a Friday morning. I put something in here. Sorry. Any questions? Besides, did you have your cup of coffee this morning?
Nope.
Okay, all right, fair enough. If we take a look at this file, you have to make sure basically that you're viewing. Now, we did talk about setting up your environment with File Explorer. Everybody recalls this, yes?
Yeah.
Yeah, so normally when you save, if you save a file extension, if you don't know that there's a file extension there with Notepad that's .txt, and you try to run the HDL and it reads .txt, the simulation environment isn't going to know what to do. In some cases, you have to click on this and then change .txt to .htl in order for it to run. Now, I'm going to go ahead and run the hardware simulator, and I'm going to do it from my desktop. There's actually should be a link. No, is there not a link? Okay, I'm going to put a link. So we'll be doing this a lot. It might be helpful for you to select this, right-click this, send to the desktop a shortcut so that it's always there. Okay. Any questions so far? And where's my Nanto-Tetris shortcut? Okay, so I'm gonna put this here where it's nice and prominent, and I'm going into my tools. And does everybody see built-in chips?
Yes.
Okay. So let's take the AND HDL. I'm going to open the AND HDL, and I have to know where that thing is located. So when I start the hardware simulator, I'm going to have to point my file finder or browser to the temp folder first, then Nanto-Tetris, then tools, then built-in chips. And these are chips that are provided on behalf of the author in the Nanto-Tetris software. Now, you may not be seeing the Notepad icon when it's listed on your screen. And if you do not see the Notepad icon, what I want you to do is I want you to right-click this and select the Open With option. And then I want you to select the Always Use This app. And if you don't see Notepad, I want you to click More Apps. And I want you to find Notepad and select it. Make sure the checkbox is here and Notepad is there. Now, there is another way to change the file association. If you know that, good for you. Okay, but what you're going to do is change the file association. The icon should change. And when you double click on it, more importantly, the code, the HDL file should open up and you can see what's going on. Now, as you walk through the orientation, In the links, one of the things you'll discover is that a double forward slash is a way of commenting out a line, or a slash asterisk is the way to start a number of lines that are commented, as long as you end with a asterisk slash on the other side, the reverse of that. So anything in between. It is typical in the header of the HDL file to explain things. And it's really important that as you customize your digital components, your logic gates, you're going to want to change it so it reads by, and you're going to put your first initial, last name, and then the date. The other important thing to note is the logic that's in there. We're going to be dealing with some pseudocode quite a bit, and we want to be able to make short, concise statements of what a thing does. So what we're going to say about and let's check the logic here. This presumes that you have two inputs and one output going into an and logic gate. Is everybody with me?
Yes.
Yes.
So we have a chip. It's a very simple chip. It's actually one of the simplest in the world. We're only using one of the three fundamental logic gates. And that logic gate has two inputs. And that's the lowest number of inputs that an and or an or can have, because an and or an or has to compare one value to another. And if you don't have a second input, you don't have a comparison to function with. That's one distinction that's also unique compared to not, right? Not has just one input and one output. So we have an A and a B input. Now, I loathe the use of single letter variables in programming. I can't stand it. It just drives me bonkers. We should be using very descriptive variable labels, right? Whether they're input variables or output variables, we should be using descriptive names. And that's a good practice. That's a best practice in every programming language there are. The only problem is that everybody in the industry that's trying to make it quick and easy for people to write a little bit of code without making too many mistakes is to keep the variable names simple, so they stick to one letter. And the only other problem that poses is that everybody's algebra gear in the back of their brain kicks in. And what we need to understand is that in programming, as you well know by now, this is not the same as an equal sign in an algebra equation. Rather, it is an assignment operator. Okay? So whatever's on the right side of the equal sign is fed into and stored in the other side, right? And that's what happens, is that we're operating from right to left. Whatever's here gets moved into there. And if it's just A and B, and every little logic gate you have 47 logic gates and they all have inputs A and B. Could that get confusing? Hell yeah. Okay, now that's just my little rant about label inputs. Now, what do we want to do for the purposes of your solutions? We do not want to deviate from the examples that are shared in Nanto-Tetris because it's going to simplify our troubleshooting initially. Later on, we can foray into the wonderful world of best practices for HDL coding. And HDL coding is also very different from other programming languages. It is a simulation that lists the chip components and what they do, but the order of listing is unimportant. The order listed is not important. In a programming language environment, the order something is listed is critically important. And so that's something that I'd like to share with you about this environment, okay? So we have two inputs named A and B, and we have an output. And we're going to call the name of the output out. And so this logic statement reads out equals 1 if A equals 1 and B equals 1. Now, I didn't state that correctly because, well, that's really more like the equals. What it means is that A is equivalent to 1, or B is equivalent to 1, or B is equal to 1, or A is equal to 1. The double equal actually means equal. This does not mean equal. Does everybody understand what I'm saying, or am I confusing people?
Yes, I understand.
Yeah, we understand.
Yeah, at this point, you should have been engaged in some level of coding course. Okay, now, unless In every other case, for A and B, it's 0. So that's a very short statement. And the components of this chip basically include a built-in AND chip that's written in Java. So this HDL simulation is going to use a built-in chip component, and it's going to call a built-in chip that's written in Java, which is why you need the JRE environment, okay? Any questions so far? I want you to remember this. In fact, I want you to click on this, and if you're not following along and doing it as I do it, it might be a good idea to follow along and do it. I'm going to press the control key and tap C so I can capture this path, because I want to remember where this is, okay? I'll minimize this. I'll go into my NAND to Tetris folder, and I'm going to back out a little bit. I'm going to go into Tools, and I'm going to go to the Hardware Simulator. Now, if you're running Linux, you would run this with permissions from probably a hashtag prompt or a pound prompt, root privileges, in order for it to execute. And you'd have to have the execution permissions turned on for this. If you use Linux, you know what I'm talking about. If you don't, you won't. But this also works on a Mac. So if you have a Mac, you can open up Terminal on a Mac, and then you can basically enter your password, get a pound prompt, change the permission so it's executable, and we'll show you how to do that if you have a Mac. So if you're Linux or Mac and this isn't running, you're okay. What I want to do here is I want you to select this hardware simulator.bat, and if you don't have .bat, it means you're not showing the file extensions, but I want you instead to right-click this and run as administrator. Everybody with me?
Yes.
It's going to be a pop-up that says, do you want to make this, you want to allow this app to make changes? You're going to say, yes, okay, I do. You'll see a black screen flash, unless you're spoiled rotten because you have a wicked fast computer and the black screen flashes so fast you can't even perceive it with a human eye. If that's the case, congratulations. But please don't rub our nose in your technological prowess too often. All right. So here is the basic hardware simulator environment. And what I'm going to do is I'm going to load the HDL file for a basic, because this is what I have to do. For my solution, I have to download, unpack, set up a simple folder, and then I have to go through the steps that the author walks through. But then I also have to do this and load a chip. So I'm going to go to I'm going to open a file, an HDL file. That's what this means. Load a chip means open an HDL file. And of course, it opens in my documents, which is a pain in the neck. And this is another reason why I like putting things in the temp folder, because it doesn't matter which login you're using. You can basically go to the C drive and then go from there into temp, and then go into NAND to Tetris, and then go into tools, and then to go into built-in chips. And now I'm going to load AND HDL. Does everyone see my screen?
Yes.
Yeah.
Yes.
Now the screen real estate is an issue because you want to display this down here. If you're using a certain client and you don't see this bottom strip, that's a disadvantage. You'll also notice down here that if I'm running this thing, a little Java logo will appear, which means that it's using that JRE we were just speaking about. This is where the HDL displays, but you cannot, let me say again, you cannot edit. You can only view the HDL file. But this is useful because then you find out, oh, I did this. This wasn't provided by Nissan and Schocken, the MIT celebrated authors. This was my doing, right? So whoever did the thing, the file name and where it's supposed to be, those are important pieces of information. Because when you're troubleshooting and you get an error, you want to know where the file is, where the path for the file is. And there can be differences between what's up here and what's listed in here. And that can be a clue about what's working wrong. When you get error messages, you're going to see them down here in red. And the problem is that if you have it configured like this, You won't see the red down below, and it just won't run. What will happen is that this won't load. You won't see input pins, output pins listed. But I want you to notice here that the value is 0 and 0 for A and B. And I want to make sure this is working right and my simulator is working right. And so that's the other part of our solution that you have to demonstrate in order to log full credit. So I want to make sure that when you're showing your screen that you capture, you include the bottom margin so that if there are errors that display, right? I want you to use a simple logic gate like and, or, and not. You do not have to use and. In fact, I'll be impressed if you use or, okay? But what I want you to do is to click into the value table, into the value side of that entry, and I want you to backspace over it after you double click into it, and I want you to enter the value 1. Now, I'm going to run this thing. So if I step through each line of the HDL, I can use this function, or I can just run it. And I'm going to run this with the input value 1 for A and 0 for B. Is everybody with me?
Yep.
Yes.
After I click run, if this is functioning correctly, this should not be grayed out anymore and the value should change. Now, who would care to predict what the value output is going to be? Value of the output is going to be. And why? Based on the logic we've already reviewed. Okay.
But are you asking, the value would be 2, or you asking if it would be true or false?
Yeah, I want to know if it's true or false, 1 or 0. It's going to come out 1 or 0. 1 if it's true, 0 if it's false.
True.
Okay. So I have an input value in A of 1. I also have an input value of B of 0. And this is the AND operator. What do we know about
Yes.
what do we know about the logic, the value of the logic, the way the logic works for an AND? And I'm very glad that you answered, okay? Because actually, I'm very glad that you answered because you're not correct. Because this is false, because there's one input and there only has to be one input with a 0. When I hit run, this is no longer grayed and the output is false, right?
Yeah, mix up my or and and.
Yeah, exactly. Yeah, exactly. That happens a lot because we're verbally thinking and we're thinking about the addition, right? And that creates a mental block. And that's where we have to think out loud and we have to do this on a basic level a few times over and over again until it sinks in. It's kind of like learning how to ride a bike. The skill sets are different. You have to master them and become proficient with them until they're reflex. Because if you don't, and you're trying to think about what you do on a bike when you're slow, you'll fall over. Does everybody understand that analogy?
Yes.
Same thing with swimming. If you're not moving in the water, you're less stable in the water. You're kind of like sinking in the water. Of course, that doesn't happen here because we have very salty water. I'm going to enter a value of true or 1 for B. And I want to see what happens if this AND is functioning properly. If it's multiplying correctly, I'm going to run it. And what do we predict now for the value?
It'll be 1.
It'll be 1. So I'm going to hit run, and sure enough, it changes to 1. Now, which screenshot do you paste into your solution when you submit? I don't care, either one. I want to see if A is 0 and B is 1, will I get a 0? So I'm going to change this, make this a 0. I'll reverse it, right? I'll change the 1 to a, I'll hit enter on my keyboard. Now I have 0 for the A input. B is true. I want to run it. And sure enough, the output is false, right? So if just a single false presents or 0 presents, the output's always going to be false, right? So this is what you need to capture for your solution. It shows me that your hardware simulator is working. It shows me that if an error shows up, you can see it. And it also shows me that you know how to load a chip, which is basically to open a file and you know where this stuff is, okay? Any questions about what you need to do to complete your first solution? It's actually pretty easy. Now on a Mac, it's a little different. You run this script inside a terminal, and as long as you have permissions, you can do that. If anyone has a Mac and they'd like to walk through that after this class, or you'd like to set a time, let me know, okay? All right, so where do we go next? Here is what we're going. Please remember, take the time to walk through the hardware simulator tutorial that's available from our authors. Really rich, really cool stuff, tells you a lot about the environment and how to work with it. And we're going to get into it more and more. With each solution, you'll be doing progressively more and more interesting things. Even though this is a very long PowerPoint, do not let that deter you. Just get as far as you can. Get as far as you can. And then as we flesh out more about logic gates, more of this will make sense. You'll go back to this over and over again, which leads me to a moment of prayer I need to have with everyone in the class, okay? In previous seasons, I've received feedback from students and they say, oh man, we're still going over the same stuff and it's 3 weeks later, right? So I've received constructive criticism from students at the end of the course, and we're always interested in improving our instruction. But one of the things that I want to impress upon you this morning is that we do crawl, walk, run. It's an iterative thing. So we get into the simulation environment, right? And we do some baby steps with the simulation environment. And then a week later, we take it to another level. And so if you're away for 2 or 3 weeks, let's say you're off island or something, and you come back, and then you tune in for a minute, and it looks like, oh, we're still on the same, we're still doing the same stuff, right? Yeah, it's called a spiral curriculum technique. It's iterative, meaning cyclical. We get a layer deeper each time. And this is the flavor that you're going to get when you go through the slides here. We're going to refer to this throughout the entire course. Doesn't mean we're doing the same thing over and over again, but what it means is that we're going to get progressively richer and deeper and richer and deeper and richer and deeper and richer and deeper and richer and deeper until you're screaming. And it's going to be a lot of fun. But if you tune in for a moment and you're not aware of how that process works and what we're doing, actually, it may look like, oh, okay, we're really not talking about anything different. And we could be on planet X by that time. Just a word to the wise before we finish today, okay? Any questions about that? All right, so hearing none, what I'd like to do is, all right, so remember the study guide addendum, I did post that into our yeah, and I don't think I gave you an example of a Boolean function yet. So we're gonna take a baby step where that's concerned. So I haven't posted an example of a Boolean function yet, but I will before too long. And then the study guide will be study guide addendum revision 1. So as I add things to the addendum, it'll be revision 1, revision 2, revision 3, and so on. Alrighty. Let's talk about the bit shift method. So we've implied some calculation interests. We said that and is actually multiplication and or is actually addition. But there's a very cool thing that you can do with binary values in mathematical terms. You can shift a value a place to the right or the left. So I'm going to skip over the hexadecimal stuff, but I just want you to jump down with me to section E and F, right? In your study guide. Everybody with me?
Yeah.
Yes.
Okay. I'm hoping that this color coding is useful. If the color coding is not useful, I need you to tell me. But so far I've had some pretty positive regard for that. So let's look at the bit shift thing, right? So leading zeros are usually dropped. This value can be expressed like this. And it's important to understand that if you don't have an 8-bit value, it's implied that the values to the left are zeros, right? So this number in binary terms is the same as this number. Now, if you have a number like this, okay, we're going to tell you that oftentimes when you're working on bit level operations, it's called, right? It's important to preserve the leading zeros, especially where there are shifts involved. If you take the values of the ones as in the exact order that they're listed, and you shift them one place to the left. Let me say that again. Look at this example down here. I have 0001, and then I have 1010. If I slide that value, the value of that binary number is actually just 11010. But if I shift it one place to the left, I'm taking this pair of ones right here, and it wants to grab my whole number there. This one and this one. And if I shift it one place to the left, it means I have an extra one here in this nibble. So now it looks like this. And this number is slid one place to the left. So the 0 is here and the 1 is here and the original 0 is here, but I got nothing here. So I have to add a 0 on the end. I have to add a 0 on the end. The cool part is that when I slide one place to the left, I double the value of the number. Let me say that again. When I slide the number one place to the left, I double the value of the number. If I slide it 2 places to the left, I quadruple it. If I slide it 3 places to the left, I increase it by a factor of 8. If I slide it 4 times to the left, I increase it by a factor of 16. So I can like multiply by doubling factors just by sliding left a place at a time. 2, 4, 8, 16. Okay. I want you to marinate on that thought. And we'll talk about what happens when you go to the right on Monday. Are there any questions about what we just covered about our bit shift? To the left, one place. That's all we did. Baby step, one place to the left. Any questions? Okay, I'm going to stop sharing. I'll stop recording.